So, hello everyone. My name is Nicholas Karnesis, and I am a postdoc at the University of Thessaloniki in Greece. And today I want to talk to you about using behavioral likelihoods for robustness against data outliers. So this idea is quite old. We used it for the analyzing the data of Lisa Pathfinder, but then for some reason it got forgotten. I think it's time now to get it out again from the drawer and use it for some nice ELISA data. So just a reminder of what we do usually in matched filtering. When we have some data set Y, which is, we assume it's a sum of the instrumental noise plus some template that depends on some parameter theta, we usually try different sets of parameters, and then we subtract it from the data and we evaluate the residuals at the end. So the aim is to have residuals with statistical properties that are the same as these ones of the noise of the instrument. And what we usually do is we assume this Gaussian likelihood, where this parenthesis here is you take the usual noise weighted inner product, which is basically the power spectral density of time series weighted by the noise of the instrument, the power spectral density of the noise of the instrument, right? Sometimes we have to fit the noise as well because it's not perfectly known. So if we have a model, we have this C now, it's not a constant anymore. So it depends also on this parameter set. So we have to estimate it from the data. Now, in other cases, there are outliers in the data, or there's non-stationarities, other non-stationarities that forbid us from using just the Gaussian likelihood, because the residuals do not follow the Gaussian distribution anymore. And just as in this earlier work from Christian Reven back in 2011, what you can do is you can, after assuming some priors for the power spectral densities, for the power spectral density of the noise, you can write down this student likelihood, where now there is this free parameter nu that can depend from the data, and it tunes basically the tails of the distribution, so it has fatter tails than the usual Gaussian one. And this is how it looks like. This is taken directly from this paper. So these dashed lines here are the student filter compared to the Gaussian one, which is shown here. So basically what you can do is you can have all these outliers in the data, where with these fatter tails, you can take them into account and you have more robust parameter estimations for your problem, right? But we can go one step further, right? We can produce, we can follow another way, or we can go one step up and use what they call these generalized hyperbolic functions. And these can be considered as the mother of exponential distributions, because basically it has all these parameters, alpha, beta, delta, and mu, where tuning them, you can arrive to different families of distributions, like the normal Gaussian, or the student D, or the Gaussian. And the idea is that you can use this likelihood function, and together with parameters of your signal, you can get all these parameters of the distribution, where you can characterize the statistical properties of the residuals or the noise of the instrument, right? So it's been used in economics quite a bit, because they have all these weird distributions that are skewed, that they have all these fatter tails. Now I'm having this I stole this picture here from this PhD thesis from Browse, and I mean, it looks like it works pretty well. Now I don't know what are the labels of these things. I just saw time series and histograms. So, but we can use this in our case, and we can adopt this for our problems in data analysis with Lisa. Now, if we have a univariate random variable, like let me move my face down here. I hope it will be better. We can write this distribution like this, and we can simplify it even better. So we can drop the generalized from the generalized hyperbolic and keep only the hyperbolic part by removing the mu. So this is a zero mean, and also removing the beta. So the beta tunes the skewness left or right of the main mode of the distribution. And then we have something that it's more simplified. And what you can do basically is that you can, after after doing your estimation and estimating alpha and delta and beta and all these parameters of distribution, you can plot this shape triangle, as they call it, and place a dot of depending on those parameters that you have estimated. You know, this chi and xi are some combinations of these alpha, beta, and delta parameters, and you can say a lot about the distribution of the noise, right? You can say something visually. It's a visual tool, at least to see that it's nice to have. And that's one way of getting information about the residuals. Right? Now, if we write the logarithm of the likelihood, we can write it like this. And in case where we have multiple data channels, we have to write it like here y, and y here is the usual noise weight and inner product, but now written in matrix form because we have multiple channels. So this S here is a matrix, is the cross-spectral power density of the noise. I forgot to mention that this K is the modified Bessel functions, right? So you have to calculate these at its evaluation of the likelihood as well. And we can try to apply it in some simple cases. So the first demonstration is just a very, very silly toy model that I have devised just to help me also understand how to use this. So I have injected a some Gaussian in some with some Gaussian noise that has a bit of outliers, right? So it's not Gaussian anymore after this, and we have to estimate the posterior for the parameters of the sine Gaussian model and also alpha and delta and see how it works. See, here is how the data set looks like. So here, for example, this the data depart from Gaussianity. You see all these outliers here compared to the theoretical model. And here I have plotted the power spectral density of the data. So red is the injection of the signal here, and the dust gray is the normally distributed noise of the instrument, and here with gray solid line is the power spectral density of the data that I have used. And as you have seen, it's like having all these outliers. We have kind of a power that has built all over the frequency range of our measurement. So that's why I have chosen 3 types of analysis in order to compare this idea or to test this idea. So first, I have assumed the Gaussian likelihood where the noise is assumed known and at the wrong level, here written here. Then with yellow, I keep the colors here because I'm using them in the kernel plots later. So I have the Gaussian likelihood again, but now I'm fitting for the noise. And this is why. So now the noise depends on some parameters. Theta, basically just a level. And then I have the hyperbolic likelihood where the noise again is assumed known and at the wrong level, but we have all these alpha and delta parameters that we hope to compensate all this erroneous assumption with, right? And this is how it looks like if we run your MCMC chains on this problem. So you see the gray, which is the normal Gaussian filter assuming this Gaussian likelihood which is wrong. You see that it underestimates the errors of the distribution, while you see the red and the yellow, which corresponds to the hyperbolic and the Gaussian, while it's fitting for the noise, they seem to overlap perfectly, almost perfectly on top of each other, right? And then if we take the alpha and delta of this that we have estimated and we place them into this shape triangle, we can get some interesting results about the distribution of the residual, which is Gaussian, as we would expect. So this works pretty well, but we can try to apply it in more interesting examples. And one of them is using compact galactic binaries. Now, this is again a toy investigation, so this is not a very complicated simulation. I just took the noise power spectral density of the analytical one, generated some data on top of it, and then injected the signal of a verification binary, which is tuned a little bit to be a little bit louder, just for having clearer results. And this is how it looks like, right? So we have the gray. You can see the power spectral density of the data. This red line here is the signal. It's very well localized, and this is a zoom in. So the figure below is a zoom in of the signal, and I have assumed 2 noise levels. One is the correct one, the black one, which corresponds to the data that I have generated, and also the blue one is the wrong noise level, which I'm using to do the test, right? I'm assuming, I don't know the noise, so I'm just pretending. just like we did before with the sine Gaussian toy problem. Again, the same thing, Gaussian likelihood, wrong noise level, Gaussian likelihood fitting for the noise level, and then hyperbolic likelihood, assuming we know assuming the wrong level of the noise, but also having these extra parameters to fit. Now, this is slightly more complicated because I have written it in matrix form because we have two channels, but this is just for showing the idea. And this is what it looks like. Again, we see the hyperbolic, the red or brown color, and the Gaussian, the yellow, where we fit for the noise level. We see that they almost perfectly overlap on top of each other, and we see that the gray one, which corresponds to the Gaussian likelihood with assuming the wrong noise level, it's underestimating the error bars of the parameters of the posteriors of interest. And again, we can draw again the shape triangle that we get information from that gives us information about the residuals. So it works, it really works. And at least for this simplified case, I mean, this is a very localized type of source, so in frequency. So, and it's pretty high SNR. So things will get more complicated when we have sources that travel across the frequency band of LISA, for example, like massive black hole binaries, because then, for example, we might know the noise differently, different parts of the spectrum. So this have to be taken into account when we do analysis like this. So, but in these first toy cases, this looks pretty well. So we also got some preliminary results for supermassive black holes, but we need a little bit more carefully to design the experiment also to present the results. That's why I have chosen to present only the simple cases now. And next on the list is to analyze the split data, which I hope it will work nicely using this robust filter. So yeah, this was the idea. I hope you enjoyed it, and please don't hesitate to contact me if you have any question. And so hope to see you soon.